Hello and welcome to the first webinar of the year for Ceramics Expo 2021. It's fantastic to see that well over 300 of you have registered to join us today. My name is Callum Gibson and I'm the conference producer for the event. This webinar is entitled Understanding the Benefits of Advanced Ceramic Materials for Withstanding Harsh Environment Applications. I would like to thank our kind sponsors, Kennametal and Cerion Nanomaterials, for their support of this discussion. There will be a brief presentation from the European Space Agency, followed by an interactive panel discussion, so please feel free to enter your questions via the Q&A box at the bottom of your screen. I will now hand over to our discussion leader, Landon.
Yeah, thanks, Callum. Good morning to everybody here in the United States and to our friends in the European Union. Good afternoon. My name is Landon Mertz. I'm the CEO of Cerion Nanomaterials. Here in the United States, we're one of the largest for designing, scaling up, and manufacturing nanomaterials. And we specifically provide metal oxide, and ceramic nanoparticles to companies who are developing products. I have the pleasure today of moderating our discussion around ceramic materials and harsh environmental applications. And I was drawn to this particular topic because there are a number of advanced materials and, of course, nanomaterials that really are addressing needs that can't be met through conventional means. And the scope of our discussion today is going to revolve around space applications, which it quite possibly represents one of the harshest environments that ceramics have to operate in today. And so we've assembled a panel of some of the trailblazers in this field, representing both the users, in this case, the European Space Agency, and then makers, in this case, CeraNovis, to really hear about these next generation materials. And we'll have an opportunity to follow them on their journey of getting those materials into space. And so with that, I'll let our panelists introduce themselves. And Adrian, why don't you go first, and then Yuri and Frank.
Yeah, thanks, Landon. Hello, everyone. So my name's Adrian Tighe. I'm a materials engineer in the European Space Agency, based in the Netherlands, in the European Space Technology and Research Centre called ESTEC. I've been working for ESA for about nearly 20 years now. And my job is to provide technical support and quality related to support to all of ESA's space missions. I mean, to help them, help them when failures occur, or help them to select materials and define processes, and to qualify and validate materials and processes, to enable the space missions to fly. I'll say a bit in the presentation, a bit more about ESA and what we do in the first few slides. So I'll hand back now to Landon.
And Yuri.
Yeah, thank you, Landon. Hello, everyone. My name is Yuri Butenka. I'm materials engineer in ESTEC. So my responsibility include space environmental testing in simulating space environment. So I test different materials, including ceramic and polymers, solar cells, so everything which is related to spacecraft. And plus to this, I perform failure root cause investigation involving different surface analysis and also bulk analysis techniques available in our laboratory. We have a very wide range of instruments to perform very detailed investigations. Yeah, thank you.
Okay, and last but definitely not least, Frank Meyer.
Thank you very much, Landon, for the nice introduction. My name is Frank Meyer. I'm from Germany, and I am by training a physical chemist. I'm leading CeraNovis. We're an SME based in Saarbrücken, Southwest Germany, and we are busy in the field of producing, developing, and applying ceramic coatings for harsh environments, especially when there's a lot of heat or corrosion or ultraviolet radiation. That's where our coatings can be found. And today, of course, we're going to focus about applications of ceramic coatings in space. And it's a very good opportunity to show what new ceramic materials can do under very harsh conditions. And I'm looking forward very much to that webinar today. Thank you, Landon.
Great, thanks, Frank. And so for our audience, I just wanted to cover a few quick housekeeping items. The first, if you find value in the webinars that have been produced by the Ceramics Expo, I really would encourage you to consider attending the live show, which is going to be happening late August of this year. In my personal opinion, and I've been going for a number of years, really the breadth and the depth of the event really is bar none. As Callum mentioned, our agenda for today, we have about 60 minutes. You're going to hear a 15-minute presentation from the European Space Agency. And then as a panel, we're going to dive into 3 core topics, one around product development, another around environmental impacts for ceramics, and then ultimately potential modes of failure. And thereafter, we're going to open it up to Q&A for the audience. And this is where you guys come in. So as we're doing our presentation today and as we're having our panel discussion, I really would encourage everybody to post their questions so that we can get prepared and organized for which ones to field. We're going to do our level best to get as many of them in as possible. And you're going to be able to do that by clicking the Q&A button, which is on your Zoom meetings dashboard. And so with that, let's get the show on the road. I'd like to invite Adrian from the European Space Agency to make his presentation.
Okay, hey, thanks, Frank. So I'll just share my screen now to make sure everyone can see. Okay, now I should be sharing the screen. I'm just going into the presentation mode. And we should be good. Landon, can you just verify we're good to go? Can you see my screen?
You are good to go, Adrian. Right.
Okay. Just give us a shout if anything goes wrong during the presentation. So yeah, the broad topic today is, I've just called it Ceramics in Space. I say in more detail, Yuri and myself are working in what's called a Materials Physics and Chemistry section within ESA in Noordwijk in the Netherlands. This is one of the technical support sections within ESA. And today, I mean, we work with many different European companies. Today, we're doing this presentation, as you just heard, with Frank Meyer from CeraNovis, based in Germany. A very, very brief overview of who we are. Well, we're ESA, the European Space Agency. There's 22 European member states. There's about 5,000 employees working directly for ESA. As I say, there's many, many more people working in the companies that we work with. And we're helping to enable the exploration of space, to put it very broadly, and exclusively for peaceful purposes. So we're not really involved in military applications. It's mainly just for scientific and discovery purposes. Our headquarters is in Paris, in France, but then we have 7 different sites around Europe, related to the sort of technical development and testing of the satellites. That's mainly done in ESTEC in Noordwijk in the Netherlands. And then we have an operations center in Germany, sort of scientific center in Spain, and operations center in Italy. And then also the spaceport in French Guiana, where we actually launch the satellites. The revenue is around about 7 billion euro per year. I say that's the money that ESA gives out to the the European industries in order to enable. We give out the contracts for the industries to build the satellites. And ESA itself, all the employees are, like myself and Yuri, we provide the detailed technical support as well to the industries. So today, as Landon just touched on, we're going to talk about how ceramics can be used in space. We're actually involved in all sorts of different materials. And one of the first things we have to look at is the space environment itself, and how that's affecting the materials and what you may need to do in order to qualify the materials for use in space. So just give you a very broad overview here of what's a very quite complex subject. So firstly, you may have materials encountering high temperature and thermal cycling. So say the satellite is in orbit around the Earth, it's illuminated by the sun, and then it goes into the shadow, and it may do this tens of thousands of times over the course of a mission in Earth orbit. And the temperature of a material may go from, say, minus 150 degrees Celsius to plus 150 degrees. But then it can go even hotter. Say we'll talk in a bit more detail about mission, say, to the sun or the inner solar system, and then you can get even higher temperatures up to 400 or 500 degrees. Then you have in Earth orbit, you have what's called atomic oxygen. Maybe if you want to know more, you can ask me some more questions about this later. I won't go into the details now, but it's basically the remnants of the Earth's atmosphere in Earth orbit. It's highly corrosive because oxygen in atomic form, and that can degrade the materials on the outside of the spacecraft. Then you have high energy radiations, either in the form of UV radiation or electrons and protons. And again, materials on the outside of the spacecraft. And then for the electrons and protons, especially electronics components, can be severely degraded by these higher energy electrons and protons. And you don't have the effects of the Earth atmosphere to shield them. And so that's why the degradation can be that much more severe in the space environment. Of course, then you have vacuum, so just the absence of air, and that can cause what's called outgassing. So molecules can actually release from the surface of the materials. Maybe not so much problem from the material itself, but the outgassing molecules can then deposit on nearby surfaces, maybe like a telescope mirror or an optical instrument, and that can cause degradation of these instruments. And yeah, as I say, and then that's related to the contamination effects. And then also as we go and explore, say, the planets, or you may have heard that, now the space agencies are wanting to go back to the moon and to Mars. And of course, then you have different types of environmental effects, such as dust contamination, that we then also need to be concerned about. So why use ceramics in space? Well, firstly, because as I said, the vacuum compatibility, they have what's called very low outgassing, so they don't tend to release a lot of vapors that sort of like organic materials and plastics might do. And one of the primary reasons is they're very thermally stable, and even the sort of coefficient of thermal expansion can be very low. And this is very good if you want to, fly very stable optical benches or have stable telescope mirrors, which are very stable across a wide range of temperatures. They can be lightweight. They're not the only material which is lightweight, but that is an advantage. And then maybe for the ground-based applications, one thing is maybe you're most familiar with is the high temperature performance. And say for the missions to the inner solar system, that can be a great advantage, especially for the coatings. They can be hard, and then they have very good chemical resistance. And let's say for things like the atomic oxygen, that can be a great advantage if you have a ceramic coating on the outside of the spacecraft. And then they can have tunable properties, so you can make them white, you can make them black, and that can be very useful in terms of trying to control the thermal balance of the spacecraft. But, and it can be quite some big buts. I mean, as you probably know, if you're working with ceramics on ground, they're brittle, and they're still brittle whether they fly in space or they're on the ground. And this can bring difficulties in terms of not being able to repair them. And then you have to, they have very stringent fracture control requirements. So you have to make sure there's no micro cracks or anything in the ceramic, and you have to make sure that they'll be able to survive the launch load. And then, you need to take great care during the manufacture on ground to make sure you get no mechanical damage before launch. I've just shown a nice picture here of the Space Rider, which will be ESA's reusable space plane. And we're looking here at composite ceramics, carbon, silicon carbide structures to insulate the outside, much like the space shuttle in the early days, to make sure it'll survive repetitive re-entries into the atmosphere. I'll now just go across a few quickly applications. I say one of the main applications ceramics is in the large telescopes, and so we use silicon carbide. A recent example is the Herschel Space Telescope, and we've flown a few other missions, large space telescopes, using silicon carbide. Has very good thermal stability and very low outgassing. And this is just to give you an example. Maybe Yuri can give you some more detailed explanation of this, of what we had to be looking very much detail, say with the SEM at micro cracks in the silicon carbide before we use it for space application. Then we have some very special, okay, this is what's called a glass ceramic. This is a sort of proprietary ceramic that we call Zerador, which again, we use in space optics because of its very low thermal expansion, and also because it can be made in a very pure form and very homogeneous throughout the bulk volume. And it has a very high strength, and it can be polished very well. And so this is an example which was used in ESA's LISA Pathfinder satellite of some of the optical elements, which can really be kept very stable and have very good sub-micron alignment. Then there's the coatings. We can talk about that in more detail later. Say white ceramic paint coatings, and then as I say, on the ESA's Bepi Colombo spacecraft, this is where Frank and CeraNovis were involved in making white ceramic coating for the high gain antenna, and we call this V14. And then we also use this Nextel alumina cloth, high temperature ceramic blanket to cover the outside of the spacecraft. It can also be used, ceramics can also be used in the electric propulsion thruster chambers, because you get very high temperatures in the thruster chamber itself. And it's about like sort of aluminium nitride cable clamps, and a few other technical ceramics can be used on the walls of the thruster. And then going towards the future, now this is more of the advancing field, of course, additive manufacturing. We started to look at different ways where we can use additive manufacturing to make different types of ceramic components. And this for sure will see more application in the future. And even making lunar bricks, you know, in terms of in situ resource utilization, to use the lunar dust and sinter it with sunlight, and the idea would be to make these lunar bricks in situ on the surface of the moon. So say Frank is here with us today. He works for CeraNovis, was a company which ESA was working with to make high temperature resistant ceramic coatings for the Bepi Colombo spacecraft. You can ask Frank some more questions about the company itself. But it's specializing in different types of high performance ceramics and coatings. And as I say, space is one of the niche areas for this type of company. The coating we focus on today is called Nanovation V14. And why ESA chose this coating? Because it's a very highly stable coating, which stays as white as possible, because it's to be used as a thermal control coating to reflect the sunlight and keep the spacecraft as cool as possible. And it also doesn't degrade so much under UV radiation. And again, it's based on an alumina. That is basically the main composition is alumina. It can be applied by spraying with various different curing conditions. And for Bepi Colombo, we applied it on a titanium substrate for the high temperature performance. Has very, very good adhesion and very good properties. I say it's very stable, doesn't outgas, and it can also be sealed with a thin glass layer to make it even more resistant to the space environment. And then Yuri will also answer any questions about the testing analysis. We did a huge amount of testing, testing this coating up to 400 degrees Celsius under vacuum, up to 10 solar constants, and did a huge amount of different surface analysis and physical and chemical analysis on the coating to make sure it will survive the harsh conditions at mercury. One of the concerns was that it did tend to darken due to the combined effects of contamination and VU radiation. And then we developed with CeraNovis, a proprietary process in order to protect the ceramic coating even further from the effects of the space environment. And this is all like to show this nice files. Okay, on the left, these are in-flight photos taken from the camera on Bepi Colombo as it's going towards Mercury. I think it will reach Mercury in about 4 years from now. On the left, you see the nice white ceramic coating on the high gain antenna. And on the right, it's just a nice picture. You see Venus traversing across the field of view of the spacecraft as it makes its way towards Mercury. So yeah, just to sort of take home message, I mean, technical ceramics have quite wide use in space applications for high thermal performance, radiation and atomic oxygen resistance, and especially the thermomechanical stability. And here's just listed there a few of the more common ceramics which are used in space. But you have to be careful because they can be difficult to repair due to their brittleness. And as I say, you need to take great care handling them on the ground. And within ESA, we're always interested in different areas of, new research and development related, especially to smart materials and coatings for environmental protection, and say materials for heat protection systems, additive manufacturing, and we're even looking at different bio-inspired composite materials, say based on synthetic mother of pearl for some advanced applications. So that includes the presentation. Yeah, you can find out much more on our website and esa.int, and also this ideas.esa.int. You can actually put forward your own ideas if you have ideas of using your own materials for space application. So I'll finish the presentation there and I'll stop sharing and I'll just hand back to Landon.
Okay, great. And we're going to bring back our panelists. And Adrian, thank you very much for the presentation. To our audience, just a very quick reminder, post questions often as we move through this panel discussion. And when we get to the audience Q&A portion of this event, we will get to as many of those questions as possible. So gentlemen, let's talk a little bit about application development. And Adrian, for those in the audience that are new to space, how do ceramic coatings protect materials from the environment in space at kind of a generalist perspective? And then I promise I'll give you a few minutes to take a break from talking.
Yeah, thanks, Frank. As I say, I mean, the Bepi Colombo spacecraft there is a very good application. Generally, the protections used in the form of a coating on the outside of the spacecraft, and they're good. So going back into the low Earth orbit, say where you have the atomic oxygen, this is very, very corrosive. So it's basically molecular oxygen in the form of atoms. And so any of the organic materials, even the highly advanced materials like the captons and all organic materials, are eroded quite significantly by atomic oxygen. But ceramics are inherently resistant to atomic oxygen, so we can apply a ceramic coating on top of the material that indeed makes it resistant. Then of course their high temperature performance means that you can use them it's what's called a thermal control coating. And this is where you see this white, like on the Bepi Colombo spacecraft, it's going to maybe some of the materials go up to 400 or 500 degrees on the outside of the spacecraft. And that's why you want to put these nice white coatings to deflect the radiation. And say if you use this like the CeraNovis ceramic coating, then that also it improves the thermal performance of the material. So that's where the ceramic is used as a sort of environmental protection material.
Thank you for that. Now, Frank, you were the material developer. You were also the coating developer. So, two questions for you. First, tell us why you decided to leverage nanomaterials specifically. What precisely were you looking for? What performance advantage? And then I guess a follow-on question for myself would be, how difficult did you find it to develop the coating formulation? And then, of course, the sintering parameters that, of course, are critically important when you're laying down any kind of coating, especially ceramics.
Yeah, the thing, the big problem was that the sintering conditions were given by the substrate. No? So we were asked or required by the space agency to find a coating that is low temperature sintering on a titanium surface. And of course, you can work with several ideas that you have behind it, but one of the ideas was to use a low sintering variant or a low sintering material. And this is a known property of nanomaterials and also of some kind of nanostructures that come when you work with silicates, for example, which turned out to be in the final formulation. And that was one of the biggest tasks, to find a binding material that works under those conditions. The next big requirement, of course, was that you need something that is basically free or very reduced with regard to organic carbon, because the organic carbon, as Adrian already told us a little bit, will deteriorate and will decompose upon irradiation. And as there is no oxygen in deep space, yeah, it's going to remind there is something as a black carbon-based species, and that's going to lead to big problems with regard to heat, which is not dissipated away, but which will be entered into the part. And therefore, the biggest task there was to find something which is low temperature sintering, which has an extremely good thermoshock resistance, because the antenna, for example, is within minutes from sun oriented, which is 400 degrees C, to the shadow of the sun, which is like minus 130 something. And you need a ceramic that goes with the metal substrate. Now the metal will expand when it's hot and will shrink when it's getting cold, and you need a ceramic that goes with it. And therefore we decided to work with something that has a very good coefficient of thermal expansion, which is equivalent to the one of the metal, which is underneath. We also incorporated a certain porosity, and therefore we used a bigger filler combined with a smaller binding particle diameter. And we also worked with a layered material like the hexagonal boron nitride, which is also in a position to act as an agent that makes it possible that the ceramic will stay on the metal base during shrinkage and expansion, when this 500 degree C temperature gap will happen within a couple of minutes. So the formulation at that point was rather easy to find when you have found the right components. The biggest task with regard to the formulation, of course, was that it needs to keep a very low alpha. So it needs to be basically white and reflecting, and it is not allowed to deteriorate to an extent that it's not reflecting heat, but that it's taking heat in. And that was one of the main goals of the development, to work with this toolbox of materials that can also be processed basically without the help of an organic additive. And that was one of the biggest challenges in development of this coating.
Yeah, it is amazing. We always tell customers, I mean, you can get an off-the-shelf nanomaterial, but that's only going to get you so far. And you really have to have control over a wide degree of parameters of the material itself. And then, of course, all the processing conditions downline. But you really can get incredible performance, to your point, by doing those kind of things. So now, Yuri, characterization of the performance down here on Earth is pretty important before you fly apart into space. And so, broadly speaking, what are some of the main parameters that you're looking at when you're testing for a harsh environment like space?
Yes, so answer to this question is related to what was discussed by Adrian and Frank. So main thing what coating, so ceramic coating and ceramic units have to survive actually before we get to the space, it's storage and also launch. So for storage, normally ceramics are quite robust. There is no problem here. But in the launch, they have to survive intense vibration and mechanical load. So this is where first ceramics has to be tested. It's on vibration test and different type of loads. Then when we get to space, we ceramic coatings would experience very harsh space environment. So this is temperature variation, what Frank mentioned, severe temperature variation. So ceramic coating and ceramic spots has to withstand thermocycling. So we perform thermocycling. Then radiation. So in space, we have radiation in our solar system, especially if we go towards sun, it's very intense ultraviolet and vacuum ultraviolet radiation, which is below wavelengths shorter than 200 nanometers. So this radiation can cause, first of all, contamination induce fixation on the surface of the ceramic. So if we have a spacecraft, it would emit some contamination. In case of BP Colombo, we found by modeling that main part of contamination is emitted by solar array. So we have to test, so simulate, test is performed by simulation, this environment. So we have representative UV radiation source, we have contamination source, and we see how coating will darken. So coating has to be withstand contamination fluxes. Then also coating can also degrade chemically, because though VUV part of radiation, so vacuum ultraviolet, is very low, but it still can induce some chemical changes in ceramic. So this also has to be observed, but it's not very common that ceramic degrade chemically. Other part, what we test, because in space there is a plasma, which normally consist of electrons or ions, protons, for example. So ceramics are not conductive, they would charge. So this has to be tested in a special test setup when we charge ceramic and see how it will discharge. This is important because charging of ceramic and then discharge can cause very severe damage to surfaces and also to equipment. So, all mechanical part of strength of ceramic is not that important in space. So ceramic has to just survive launch, and then in the space, mechanical loads are not very severe. So this is not that important. Also, for ceramic coating, they have to do not produce particles. They must not produce particles, and they must stay on the surface. So we have to test adhesion of this coating, and also we have to see whether this coating start to shed particles after testing. So this is main parameters what I mentioned. They all have to be tested and carefully observed.
Thank you. That was extremely comprehensive, and it just goes to show that it really is a very harsh environment in space that you're dealing with, just across the board. Frank, speaking of testing, I know from our own experience that when customers request us to design certain materials, one of the things we need to do is design them, characterize them, and then do screening tests on them. And the challenge is that there's only so far you can take it inside your own lab, because some customers have proprietary techniques, proprietary equipment. And so I'm curious, as you went through the product development life cycle, what were you able to do in-house, and what did you ultimately find yourself reliant on ESA to perform?
Yeah, there are there are a couple of things. Of course, this is a very unique situation. So you don't have not many off-the-shelf solutions. ESA has many different application machines in their laboratory for the special applications, but they only have a very limited amount of time and staff. So it was decided in our project that we try to do all the necessary pre-testing in our labs and only give to ESA the promising candidates, of course. Therefore, we simulated the adhesion, though there's a norm in Europe that we can work with. It's the ECSS norm. So the adhesion could be tested in-house with an absolute value in Newton per square centimeters. That could be checked. We could also check the alpha, also the absorptivity under ambient conditions. And we also had a little, we built a little high vacuum chamber which could be heated up to simulate the stability under thermal vacuum in up to 400 degrees C. The thing that we could not simulate was the irradiation with hard UV with 10 times the solar constant, or we could not simulate, of course, the bombardment with ions in space. So for this, you need a special equipment, which was done with the group of Adrian and Yuri then afterwards. But what we did, we had, let's say, a pre-checklist. So adhesion was tested, color was tested, alpha, stability, and thermal vacuum was tested. At the very late point, also, we could work in the presence of a contaminant just to find something that could be stable under very high contamination conditions. What we could also check was thermoshock resistance. So we had a little machine built where we had an oven on the one hand where we heated up the specimen to 400 degrees C, and then we had a dewar flask with liquid nitrogen very close to it, and then we dipped the ceramic from 400 degrees C into liquid nitrogen, waited for 30 seconds, repeated this for 10 times, and if the ceramic was able to withstand this temperature drop of 600 degrees C within 1 or 2 minutes, then it could also withstand the thermal expansion and the thermoshock, which is in space, which is not so harsh. So what I want to say is that we had to build little setups to simulate some of the environments, but the last say, of course, is from the agency. And then they had the validating instruments mostly done then by Yuri when it comes to a very long exposure to radiation under contamination atmosphere, which is one of the most crucial things because the white coating needs to remain white within a space time of 7 years. And this can only be simulated when you have a very special equipment, which was, I think, even constructed by Yuri, because it was not existing to that extent that you could check the exposure to radiation in the controlled presence of a contamination source. Yeah, and that was basically the biggest thing that could only be done by the European Space Agency in the Netherlands.
That's great. So again, a reminder for our audience members, and I do see questions rolling in, please post and please post often as we discuss. For our panelists, we have about 12 minutes or so to get through the rest of the panel session. So I'm going to just kind of step up this pace a little bit. I wanted to talk about environmental impacts. And Adrian, we know that all materials degrade, right, as a function of the time and the environmental conditions that they're subjected to. What are the real drivers of degradation in space, and how severe of a problem is it?
Yes, a good question, Landon. And as always with these questions, I have to say it depends. So it depends on the application. Of course, when we say, space application, it really depends on the mission and then what the driving degrading factor would be. And I mean, that's my job on a daily basis, is we don't, and this is what we're always saying to companies, people, we don't qualify materials for space, we qualify them or validate them for a particular mission. So if you have an Earth orbiting mission, as I say, probably in a low Earth orbit, the driving factor would be the atomic oxygen. If you have a mission, say we're flying, say, now the JUICE mission to Jupiter's moons, where you have an intense radiation field, then of course it's high energy electrons, which is the driving degrading factor. Maybe then the ceramics are not necessarily the best solution. But as I say, if you're then sending missions to the inner solar system where you have the high temperatures. So the Bepi Colombo solar orbiter, NASA have done similar missions as well, like the Messenger to Mercury and Parker probe. There the ceramic coatings are really coming into their own in terms of the high temperature performance. So that really depends. And then for the other applications, ceramics for the thermal mechanical stability, it's more the long-term performance and very subtle maybe changes in temperature. Like for this LISA Pathfinder and the LISA mission, they're measuring, sub-nanometer changes, dimensional changes over years and years. So then you have to really look at the long-term stability of the material. So there's a whole different range of factors that you need to consider.
Great, thank you. Now, Yuri, we're in space, we're being bombarded by ultraviolet and vacuum ultraviolet. And I've got to imagine along the way that we're also introducing contaminants into the coating itself. What kind of impact do you see on the thermal optical properties of the coating?
Main impact is caused by UV induced fixation of contamination. So if you consider contamination as a flux of normally organic molecules which originate from organic parts of spacecraft. So for example, in case of BP Colombo, it was carbon fiber reinforced plastic of solar array, which was generating molecular flux of organic contamination. So this contamination, when they reach surface of ceramic coating, for example, on high gain antenna, they can absorb, and if in presence UV and ultra VUV, this radiation can break organic bonds, because energy of radiation below 200 nanometers, it's more than 6 electron volt. So energy of covalent energy in organic molecules is about 5 electron volt. So it's in the same range. So organic molecules can break, and then what will happen next? They will can polymerize and become fixated on the surface. Next step, when we go closer to the sun, these polymerized molecules, they will not desorb because they became heavier, and they start to transform to the amorphous carbon. And this will cause severe darkening of the ceramic surfaces, which will cause very high rise of solar absorption. So temperature of this coating will go very, very high, and this can cause damage to the units. So this is main concern about UV radiation for ceramic coatings in this case, because as I mentioned before, they're quite chemically stable, not all in cases, but this is really a problem.
Okay.
So,
thank you, Yuri. Now, Frank, if we step back for a moment from space and we just talk really more about general material development, specifically ceramics, you mind providing kind of an overview how we protect sensitive surfaces for, whether it's a chemical, a physical, or radiation attack, and really what are the key considerations to get that done?
Yeah, the thing is, for protecting surfaces against attack, especially under harsh conditions, the thing that I came to learn in my experience of more than 20 years is that there's always a slight difference between requests that appear to be very comparable. But first of all, is to have to identify what is the main problem. Is it the temperature? Is it that something sticks to a surface? Is it a chemical process of corrosion? And then if you work with coatings, of course, we always try to find a solution that is based on our experience and on our heritage. And we have specialized especially on applications where there is a combination of chemical attack or physical attack with high temperatures, which means that normal solutions with organic materials, which are carbon-based, do not work. So the things that we work for which are the least strongest, are silicones, which work like 300 degrees, something like that. But if you work with liquid metals, you need to have a stability against temperatures which are up to 1000. And here in space, you need to have a stability against 500 degrees C in high vacuum with 12 solar constants, and it needs and you have 7 years that you need to simulate. Therefore, the strategy always is to find, you need a coating. Is this coating needs to be porous? Yeah. For example, for space, it needed to be a porous coating to adapt to the coefficient of thermal expansion and to adapt the thermoshock. If you would make it theoretically dense, as dense to 100% theoretical density, by filling all the pores, it would have flaked off. So therefore, we needed to implement a certain degree of porosity to allow this. In other applications, you need to have a dense coating if it's about corrosion, chemical attack, because you need to keep the chemical agents away from the metallic substrates. And if you have pores going through the coating, of course, it will be damaged. So you need to fill the pores. Therefore, all the requests need to be answered in a way that you try to find the most prominent or the biggest concern, and you need to find a solution whether a ceramic can help or not. For us personally, the biggest task always is what temperature is available. Can I sinter, or do I need something that is room temperature curing? With the Bepi Colombo mission here in space, of course, it was possible to sinter because all the substrates see 400 degrees C at least anyway that have a coating. But for many other applications, especially in space, when it's very low Earth orbit, you don't have that kind of temperature. And then you have to find a coating that can be applied with our spray technique without the need for sintering. Therefore, that is always one of the biggest problems, which is how much temperature does it see in the application, and how much temperature can I apply prior to the application by sintering in an oven or in a cabinet.
Great, thank you, Frank. So, gentlemen, we're going to move to a very fast discussion on modes of failure. We probably have about 5 or 6 minutes and really quite a long list of questions from the audience, which I know we're all keen to address. So, Adrian, no big secret here. You mentioned it in your presentation that ceramics are brittle and they are really difficult to repair, especially when you're halfway through a 7-year journey to your destination. And I think we've talked quite a bit about what can cause potential damage. My question to you is, what are the risks to a mission when damage occurs?
Yeah, so Landon, in fact, the brittleness is it's probably more related to the handling, and this is probably also just the common sense from on ground as well. If you drop your coffee cup on the floor and it smashes, of course, if you have a 3.5 meter silicon carbide, one of its kind telescope mirror, you don't want to be dropping that. You don't want to be even hitting it with a screwdriver, but these are the things that happen. This is probably for this type of ceramic material, the real structural materials where the biggest risk is. And then of course the launch and the mechanical loads during the launch. And then for those type of materials, actually, ironically, once they get into space, they're probably, okay, you have the thermal cycling, which is imparting the sort of thermal load. So that's probably the biggest risk once they're in space. There's very little structural mechanical load on the material, except maybe when you say you have a release of an item and you have a shock load. So probably for those type of materials, the biggest risk is actually on the ground, and in terms of the brittleness and the mishandling. But of course, say for the coatings and such, like ceramic coatings, there's different risks. Okay, you can even have, say, the impacts, so the orbital debris impacts, so the micrometeorites may impact the material, but then it's the thermal load. So if you have a continuous thermal cycling, you have to make sure your thin ceramic coating is well adhered to the substrate. And I think that's what Frank was saying for the Bepi coatings. We had immerse it in liquid nitrogen, put it in an oven, and really put strong thermal loads, because that's what you find happening. You get micro cracks in the coating, and then gradually they could start to flake off. And that's probably the other biggest risk once you're in orbit.
Great, thanks, Adrian. Yuri, very quickly, when you do have failure, what do you do to analyze it at a high level?
On a high level, so basically, if it is failure involving fracture, so we want to see first whether ceramic is correspond to specification. So we do elemental and chemical analysis. And second, we see whether there are impurities or what actually caused fracture. Maybe it's cracks and there are some materials which are not supposed to be there. If it is color degradation, we want to see also chemical analysis of surfaces, and this involves different surface analysis techniques. So basically everything which involves analysis, chemical composition, structure, we apply CT scans, X-ray diffraction to see whether ceramic really what it is and what it is supposed to be in specification, plus whether there is degradation caused by testing of structure and chemical composition. So this is main thing we want to see. And there was example in Adrian's presentation when fracture was really related to kind of micro voids inside the ceramic. This involved cross-section, ceramic and basically microscopical inspection. So this briefly, basically structure and chemical composition in this case.
That's great. And Frank, obviously Adrian and Yuri have talked about, mode of failure in space, but just backing out, because you obviously have a much broader degree of experience in different applications. What do you see more generally speaking, irrespective of what harsh environment you might be looking at?
I mean, the biggest failure normally that we see when we use ceramics is lifetime. Now, is this effect the ceramic gives there as long as it is needed now, especially when it's a long-term application and you're not in a position to repair. Now, for example, if you do it on a space part, it needs to be done once and it needs to last as long as the mission goes. Yeah, and in other applications where with ceramics, for example, in industrial production, where you have a non-stick coating that works 24/7, it wears off with time, and then you always need to know, is it long enough that somebody is going to use this, and when it's not long enough, is it possible to repair it on site, which is for ceramics always a big task, because normally you need to remove the ceramic. You need to sandblast it away, or you need to remove it chemically to make it new. And especially in the niche markets where we work, there normally is no precedence, so there's no experience, so you have to work completely new, because somebody always has something new, like a corrosion at 400 degrees C, something like that. And then you always have to check whether the protective effect that you give lasts long enough that somebody accepts this as some solution to the problem. That was one, from my experience, is the biggest task. How long is this effect going to last, especially when the environment is very harsh and it's not a common problem where you have much of experience from the past.
That's great, Frank. So, gentlemen, we are going to open up to questions from the audience. There is one generalist question here that I've seen a couple of times in different forms. And simply put, the space industry is a pretty difficult industry to break into. So if a company wants to work with ESA and get a part flown into space, or perhaps even go through new material development for a certain application, what does that look like?
Yeah, so shall I take that, Landon? I think, on the last slide of my presentation I gave, now ESA have this web portal, this ideas.esa.in, to where you can go to. It's got a new, because we run many different types of technology activities, so you can actually look on there. That's what I advise, and see the different ways you can actually put your own ideas on there. If you're a small company who has some advanced ceramic or some new idea, and then it'll go through some review, and then you can get small study contracts to work. And you go across the whole range. You have this TRL scale, the technology readiness level, where you can go from what the very conceptual ideas all the way up to flight opportunities, where you can actually fly the material in space. You can then also work with companies like franks, so work with bigger space companies, and maybe you provide a part and a more experienced space company would help you to qualify it for space. So there's many different ways. It's to, yeah, I say, to go onto the website. That's what I'd recommend, and have a look at the different routes there.
Okay, great, thank you. So I actually have two questions here, which I am going to combine into one for Frank. So the first is, what's the metal substrate that was used for the coating? And then the follow-on question is the spray coating the major method to coat this specific material? Can you comment on things like traditional slurries, pros and cons? And there was a comment here, maybe spraying is related to how you protect the material structure.
Yeah, the substrates that were within the mission were given from the prime and from the agency. This was basically titanium grade 5, titanium, aluminium, TiAl V64, so titanium grade 5, and also for the multi-layer insulation, it was titanium grade 2. Currently, we work on versions that are applicable on aluminium, because this is the most common metallic surface. Also substrates that might be feasible, but we are not used within the Bepi Colombo mission Adrian have described, is CFRP, or even some glass surface where you need a white coating in potentially. But most surfaces are metals like titanium or aluminium, but the need is also there for CFRP. Why was it done like that? First of all, the requirement was in a way that the coating needed to be done in a very thin way, in a very thin reproducible way. And the requirement was to keep it in the range of 15 to 20 micrometers, and it needs to be done in a manual way. So this was done by a person, not by a robot, a trained person who is a professional sprayer who trained on a dummy and then transferred that technology on the real three-dimensional complex parts. Because the parts were very complicated, you could not also work with thermal spraying or PVD or CVD or some of those things. Also, sometimes due to the size, this was not possible. So it was done with a spray paint process in a way that you can reproduce 20 microns plus minus 5 microns. And of course, you need to keep the shape of the part. Yeah? You need to keep the structure. And therefore, this was the only option. The only option was to do a manual spray painting and not working with any kind of other application methods. For some flat sheets, you could imagine doing it with PVD or CVD or thermal spraying, but for the three-dimensional parts that came within the course of the project, the only option was to do it in a spray paint version with SOPs that are so precise that you could do it in a reproducible way.
Okay, great. I see a number of questions here around, chemical protection and providing barriers for atomic oxygen attacks, which I presume obviously leads to, lower performance and perhaps failure in certain instances. Yuri, would you be able to talk about that a little bit?
For chemical protection of ceramic surfaces, what was developed in CeraNovis with Frank for Bepi Colombo, we basically sealing of the porous structure was developed, because porous structure, as Frank mentioned, they're very good because they provide certain flexibility during thermocycling of the coating, but they're also bad, as we found, because they act as like site of adsorption of contamination. Therefore, sealing of this coating was developed in CeraNovis, which provides actually kind of contamination repellent properties. So we don't have that much contamination. This was tested. And from other hand, we still have porous structure. So we combine both properties, contamination resistance and resistance to thermocycling. So in this case, this is what example when we combine both properties by modification of surface of the coating. For example, for protection for example, for electrical charging, coatings, electrical conductive coatings are used. For example, tin indium oxide. So they provide some conduction passes on the ceramic, and this protects ceramic from charging. So there are different ways how to protect ceramics and ceramic coating from space environment. But in each case, it has to be considered specifically for mission. Otherwise, it is very difficult to develop universe ceramic coating and ceramics.
Okay, great. And Adrian, a couple of questions about the reflecting surface of the silicon carbide mirror. People wanted to know, how was that done? Was that done by CVD? And then just another follow-on question, which I believe is focused on the material that was in the presentation today, is the thickness of the glass ceramic coating.
Yeah, so I think the thickness of the one Frank said, I think it was around 20 microns or something. Yeah, the silicon carbide, you can do with the CVD. It's very specialized on the 3.5 meter telescope mirrors. There's only very few companies in Europe anyway who can do that. So you can deposit the silicon carbide coating onto the silicon carbide structure. Depends on exactly the optical performance of the telescope mirror. You can also put an aluminium coating. We've done that on some of the other telescopes with a glass protective coating on top. That's the other coating that can go onto the silicon carbide.
Okay, great. And we're coming up at the top of the hour. So I have a broad question that somebody posed that I think is great for everybody to briefly answer, and then we'll wind down this discussion. And broadly speaking, this individual wants to know, what are the novel developments going on right now in space? And I'm going to add an extension to that, specifically with materials. So why don't we have Frank go first?
Well, of course, from a coating point of view, there's always a need for a conducting white coating. Yeah, something that is conducting and is white. Yeah, because most of the conducting coatings are black. So that's something where I could imagine that somebody is going to work on, because there's a need for that. And of course, I think one of the topics that might also be used is to have protection against atomic oxygen. So that means coatings that are withstanding, especially at low distance to Earth, the permanent bombardment from the aggressive species of atomic oxygen, because this might prolongate the lifetime of parts that are flying in space. And that there's more, currently we see many more satellites every week and month going into orbit. And I think if you find something that is stable against atomic oxygen or is better than what is there currently, this might be an opportunity for many companies.
Okay, great. Yuri.
Yes, for ceramic coatings, I would say main problem now is good adhesion. And very extreme properties like a very high solar, very low solar absorptions and very high emissivity. This is important for optical elements, for example, in case when you have to keep everything around optical unit very dark. So you want actually in this case to have very high absorptions coating close to 1. So this is challenge. Plus you want to this coating to be to have very good adhesion, because you don't want to particles falling on your optical units. So this is a quite big challenge for coatings inside optical units. They have to have these extreme properties, no particles, extreme adhesion, and extreme optical properties in terms of emissivity and solar absorption. So this is what I would say challenge now.
Okay, great. And Adrian.
Yeah, thanks. And yeah, so just to maybe just summarize some things I mentioned in the presentation. So now on ESA side, I know NASA also working, and also the Chinese and others on missions to the moon and Mars. So that's looking at any type of dust repellent coating, coatings that can protect against the lunar and the Martian environment is what we're looking at. And of course, now we're using a lot more commercial materials. Space becomes much more commercially driven. So it's either how to protect, commercial materials from space, or how to actually, if you have some commercial material, how you can sort of qualify that for use in space. And just more advanced materials, smart materials, or self-healing materials, 3D printed materials. This is the other type of direction in which we're looking for new technology development.
That is great. So everyone, we are 4 minutes, 5 minutes over our allotted time. So first, I want to thank our audience for joining us and for being so interactive during the Q&A session. We did get to a lot of questions, but not all of them, and we're sorry for that. Second, to our team of panelists, I have to say you really all have done some pretty innovative work, and personally I found our discussion really quite informative and really eye-opening, especially how what you're dealing with in space could potentially translate to performance in other real-world applications here on the ground. Before we go, I just want to remind everybody once more that the live and in-person Ceramics Expo is coming up August 30th to September 1st. It's going to be in Cleveland, Ohio, like it normally is. Hands down, this is the ceramics event that I go to every year. We're talking 300 exhibitors, almost 3,000 attendees, and 50 different speakers that cover a really broad range of topics that cross-cut business and technical matters. So I am personally more than excited to get out of the house after a year plus of COVID. I'll be there, as will our entire team at Cerion Nanomaterials. So I look forward to seeing you all there, and thank you again for joining us today. Have a good one.
Thank you very much. Bye-bye.
Thank you.
Yeah, thank you so much to our panelists and Landon for his excellent moderation. We had some really insightful talking points there and some great questions from the audience. As Landon says, the registration for Ceramics Expo 2021 is up and running. You can find it via our website, and that will be taking place from August 30th to September 1st. Also on the agenda, we have our very first lunch and learn session, which will allow you to interact and find out a little bit more about what technologies are available in the marketplace for ceramics. That will take place on June 24th. And yeah, we very much look forward to seeing you all there. So once again, thank you to our speakers, and we'll see you all in September.